This series is conducted as one of the outcomes of the Digital Transformation in Central Asia Conference held in Bishkek and Naryn, Kyrgyzstan on October 4th to 6, 2019. As this is an online public lecture, so all the participants connected online are requested to post their questions on the group chat so that the distinguished speaker will answer at the end. There are a couple of videos in the lecture, and we will also post the link in the group chat so that you can run the videos locally to get a better quality. We will run on the Zoom link also. Today is the fourth online public lecture on technology with one of the most interesting topics, artificial futures, intelligent robots in science and society. It's my honor to introduce the global expert on robot ethics, Professor Dr. Alan Winfield. Professor Dr. Alan Winfield is a professor of robot ethics at the University of the West of England, UWE, Bristol, United Kingdom, visiting professor at the University of York, and associate fellow of the Cambridge Center for the Future of Intelligence. He received his PhD in digital communications from the University of Hull in 1984, then co-founded and led APD Communications Limited until taking up appointment at UWE Bristol in 1992. Winfield co-founded the Bristol Robotics Laboratory, where his current research is focused on the science, engineering, and ethics of cognitive robotics. Winfield led UK-wide public engagement project, Walking with Robots, awarded the 2010 Royal Academy of Engineering Rook Medal for Public Promotion of Engineering. Winfield is frequently called upon by the press and media to comment on developments in artificial intelligence and robotics. He was a guest on the BBC R4 series, The Live Scientific, and interviewed for BBC News Hard Talk. Winfield is an advocate for robot ethics. He sits on the executive of the IEEE Standard Association Global Initiative on Ethics of Autonomous and Intelligent Systems and chairs Working Group P7001, drafting a new IEEE standard on transparency of autonomous systems. He has recently been appointed a member of the World Economic Forum Global Artificial Intelligence Council. Winfield has published over 240 works, including Robotics, a very short introduction, which has been published by the Oxford University Press 2012. He lectures widely on robotics, presenting to both academic and public audience. Please welcome Professor Dr. Alan Winfield.
Good afternoon, everybody, and it's a real pleasure to be speaking with you, and thank you very much indeed, Dr. Khan, for your very kind introduction. So let me start my presentation, and yes, I'm going to be speaking about robotics. In fact, the robotics of our lab, the Bristol Robotics Lab here in Bristol in the UK, and also about the, in fact, let me show you the outline of the talk. I'm going to start by asking the question, what is a robot, and what is in particular an intelligent robot? And then I'll introduce you to a number of the projects and robots of the lab, of our lab here in Bristol. And in part 3 of the talk, I'll be introducing the subject of robot and AI ethics. As you heard in the introduction, I'm a professor of robot ethics. And so I'd like to tell you about some of the work we're doing in particular in the development of ethical standards in robotics and artificial intelligence. So let me begin by asking, if I ask you to think of a robot, I'm sure, of course, many of you will think of a real robot, but of course, many people, many ordinary people, perhaps your family members, will think of a robot like these, like R2D2 or C3PO or Wall-E, perhaps, from that wonderful Disney movie. So, of course, real world robots, these are movie robots, as you know, they're not real. But real world robots are very different, of course, to these kinds of robots. And real world robots, and this is the first wave of robots, typically look like this. So we have, of course, robots for industrial automation. These are robots making, assembling cars. And of course, these have been around for quite a long time, around 50 or 60 years now. So quite, these were first introduced in the 1960s. We also have robots in warehousing, warehouse robots. We have robots used by the military for finding unexploded bombs, for helping bomb disposal experts. And of course, we also have these very famous robots exploring the surface of Mars. Now, it may surprise you when I say that these are first generation robots, particularly the Mars robot, but in fact, they are really not very sophisticated. They are basically remotely controlled, what we call teleoperated robots. So they're certainly part of the first wave. But the second wave really look very different to the first wave. So second wave robots, here are some examples. These are robots that would be help you in a workplace. The one in the middle that has a picture of Rodney Brooks, famous US roboticist. This is a robot called Baxter, and we call this a workplace assistant robot. It's a robot that's designed to be a kind of workmate in a workplace. We also have here a robot pet. This is the Paro therapeutic robot pet. It's actually a robot version of a baby seal, used in particular to help elderly people, perhaps if they have dementia or have to go into an elderly people's home. And then over here we have some research robots. This is a robot dragonfly, and this is a robot that we use in our lab in researching robot learning, adaptive robots. And this is what I call the second wave of robots. Now, in the second wave, we have what I call an explosion of new forms and materials. And in particular, you've seen some of these forms already. So the major feature, if you like, the defining feature of the second wave of robots is that these robots are designed to interact with humans. Unlike the first wave robots were designed to be working instead of humans, quite possibly in dangerous or inaccessible places, Mars, for instance. And those robots were dangerous for humans to be around. Now, the second wave of robots are robots designed to work up close and personal with humans. That's a big change in robotics. The second wave also includes multi-robot teams or swarms of robots. Swarm robotics is a field that I have worked in for some years. Another feature of this second wave is what we call bio-inspired or biomimetic robots. So these are robots that are modeled on either complete animals, like the dragonfly robot, or this little image here is one of our robots, which has artificial whiskers. So whiskers modeled on the whiskers of a rat. And so that's a biomimetic robot in the sense that a part of the robot is modeled on a part of an animal. these robots, second wave robots, are adaptive robots, they're learning robots. There are still not very many robots in the real world that learn. Learning is still a very, very hard problem in robotics, but nevertheless, it's part of the second wave. And finally, the second wave is also exploring new smart materials, new kinds of sensors. You can see a little picture there of our artificial whisker. Soft materials. This is a picture of a material that's based on an electroactive polymer. This is a material that will act as an artificial muscle, if you like. And I'm going to come on to this other thing here in a few moments. This is a picture of a microbial fuel cell, but I'll tell you more about that in a few minutes. So how would I define a robot, or should I say an intelligent robot? Well, my definition of an intelligent robot is very simple. That is, it is an embodied artificial intelligence. In other words, we take a physical body and we put an AI, the AI of course is generally software, inside that physical body. So for me, robotics is part of artificial intelligence. So there's a very strong link between AI and robotics. Really, robots are embodied, physically embodied AIs. And of course, also important for robots is that they can sense the world. They have sensors which can see or hear or touch the real world. And they have motors or actuators, we call them, so that the robot is able to act on and in the world. And this is an important characteristic. So really, I would say the three characteristics, important characteristics of robots are a physical body, an artificial intelligence, that's the thing that makes it intelligent, even though robots, of course, are not very smart, but still a little bit smart. And of course, they're able to both sense and act on the world. So that's really how I define an intelligent robot. So what I'm going to do now is to take you through some of those categories, not all of them, that I described in the second wave, and show you some examples. All of these are examples of robots that we've developed and built here in Bristol, in the Bristol Robotics Laboratory. So the first category is bio-inspired robots. And this is a project that we've been running for some years that we call EcoBot. And this little robot you can see on the left, EcoBot 2, is a robot that runs on food. In fact, actually, the robot runs on dead flies, the little dead fly here. And these little objects on the circumference of the robot are called microbial fuel cells. They are kind of batteries that run on food. Instead of chemical energy, they run on food. You put food in and the food is digested by a solution full of microorganisms, and we then harvest the electrons that are a byproduct of digestion in this very clever process in the microbial fuel cell. And in fact, the large robot you can see on the right is what we call EcoBot 3. And this, unlike EcoBot 2, I should explain that EcoBot 2, in fact, was famous because it ran continuously for 2 weeks. 2 weeks on a diet of 8, that is 8 dead flies, and no other energy source. The reason it stopped working after 2 weeks is because the waste products, the byproducts of digestion, eventually killed the microorganisms inside the microbial fuel cell. So in EcoBot 3, we solved that problem by designing a new generation of microbial fuel cell. It's these little brick-colored objects that you can see around the circumference of the robot. And each one of these microbial fuel cells is able to literally excrete the waste products of digestion. This robot also, in fact, worked on living flies, not dead flies, but living flies. And the flies are collected in a chamber at the top of the robot. In fact, the robot lives in a glass case, so it's in a sealed environment. And in fact, we introduce real live flies into this compartment. So in a way, the robot is a kind of robot equivalent of a pitcher plant. That's why I put this picture of the pitcher plant. So the living flies are attracted into this chamber by artificial pheromones, and then are piped. We have a series of pipes and motors that pipe the nutrient-rich solution down to 48 microbial fuel cells, and their energy is collected from digesting those flies. The nutrients generate energy, which is then stored in the robot, allowing the robot to physically move left and right across these tracks. You can see at the bottom of the robot. And we believe this is significant because it's the world's first robot with a complete artificial digestive system. Now, you may say, well, what's the use of that? That's kind of an interesting piece of science, if you like, but does it have any real practical value? Well, the answer is yes, it does, in fact. And for the past 5 years or so, we've been working on a project called Urintricity. And in fact, you can see this little movie. If you can see there's an LED, that LED is being powered by this series of microbial fuel cells. Again, you can see a picture of the microbial fuel cell on the left. And my colleagues discovered that in fact, a very good fuel source for the microbial fuel cell is urine, is human wastewater. And so we've been testing toilets, in fact, where the lighting, the energy to provide the lighting is generated entirely from the wastewater. So there's no additional power required for the lighting. And this, in fact, work is now funded and has been funded for several years by the Gates Foundation, the Bill and Melinda Gates Foundation, and also with Oxfam. We have Oxfam as one of our partners, and we've been testing toilets for refugee camps, because particularly for women at night, going to the bathroom is very dangerous. It can be very dangerous for women. So it's a real advantage to have lighting in those toilets in refugee camps. And in fact, we have a number of those toilets on field tests right now around the world. So you can see that even though this is not robotics anymore, it's nevertheless a spin out, a direct spin out with real world impact from the early work that we did on the EcoBot. So that was a couple of examples from bio-inspired robotics. I mentioned that I work in swarm robotics, and here, in fact, is a project that I was involved in, a large European Union project, where we built a series of robots, single robots, that were able to physically self-assemble. And you can, excuse me, you can see here in this movie, the three of the robots have joined together completely autonomously. There was nothing is being controlled remotely here. And the organism then transforms into a three-dimensional artificial organism. It's able to move as a single organism. And then when it's got to wherever it's going, it can then disassemble and return to a swarm of robots. So in a way, you could say that this is, we've kind of done a real world version of Transformers. If you know the movie the movies Transformers, it's a bit like that. And we were particularly interested in this project, the Cimbrian project, in the idea of a swarm of robots that could be used for search and rescue. You could send a swarm of robots into a building, perhaps a collapsed building after an earthquake, and the robots could search and explore individually. But if they were to discover, if the robots were to find obstacles or impediments that they couldn't cross, then the robots could physically join together, cross the obstacle, or perhaps move the obstacle, and then once they crossed the obstacle, they could return to being a swarm. So we felt that this was a really interesting kind of exploration of potential future search and rescue robots, using this idea of autonomous swarms of relatively simple robots. Although you can see these robots, these rather beautiful robots, are actually rather complicated, perhaps too complicated, but of course that's one of the lessons you learn when you do robotics research. In fact, we continue in the lab to do robotics research, and this is a rather nice picture of my colleague, Sabine Howard, who has taken over from me. She now leads the swarm robotics group in the lab, and she's built a swarm of these, of 1,000 of these very small kilobots. You can see, I think that's actually a dime, I think, yes. And you can see that these robots are really only a couple of centimeters tall. And in fact, Sabine, interestingly, is working on nanoparticles or nanorobots for cancer treatment. Now, these robots, of course, are far too big to be used in cancer treatment, but she's using these kilobots as a kind of model, if you like, in the laboratory to model the behaviors of the nanoparticles that she's also working on that would go into a bloodstream. So here we're using real physical robots as a kind of model, a working model of truly microscopic or nanoscopic smart particles that would be, she hopes, would be used to deliver drugs, pharmaceuticals, directly to a tumor through the bloodstream. So this is the kind of, again, rather futuristic application of swarm robotics. Excuse me, let me just take a sip of my coffee. So again, a couple of examples of swarm robotics in the lab. And soft robotics, I mentioned earlier, is very important to us. And here's a beautiful application which one of our students, in fact, invented this a few years ago. So what you see in this little movie clip is what we call TAC-tip. And TAC-tip is an artificial finger. It's a fingertip. And it is completely beautiful in my view. So the fingertip is a rubber dome. And in this little cross section, you can see the rubber dome, and you can see the black material of the rubber dome. But inside the dome, in fact, looking up into the inside of the dome is a camera. And what you see in this little image, inset image here, is the view from the camera. So the camera, in fact, is looking at a matrix of white dots. And the white dots are literally built into the rubber dome. And we have a light source, of course. And essentially, as the fingertip moves across a surface, and this surface has these little bumps on it, as the fingertip moves across the surface, you can see that the image of the white dots is distorted. And what is beautiful about this is that that what my colleagues have done is taken a very hard problem, which is making a touch sensor, to a relatively easy problem, which is image processing. So really the computation now, in order to process the data, is image processing. And of course, as you know, image processing is a relatively well-developed technology. So instead of trying to work on very difficult problem of materials that are touch sensitive, we've converted the touch problem into an image processing problem. And in fact, we went one stage further because we're interested in fact, we've had work on what we call remote telehaptics. So the idea is we would like to give a surgeon the ability to feel with her own or his own finger what the touch sensor is feeling if it's on the end of a laparoscopic instrument for keyhole surgery. So what we have in this little movie is this bed of pins, and you can see that the bed of pins reacts to the experimenter actually touching the tack tip. So if the surgeon's finger, imagine the surgeon's finger is placed on that bed of pins, then he will literally feel what the fingertip feels. And we've made all kinds of different versions of this fingertip, even small enough, in fact, to fit on the end of a laparoscopic instrument used for keyhole surgery. So this is, again, a beautiful example of smart, intelligent sensing device that we've developed in the lab, again, with real-world applications. Another example of soft robotics is the thing on the left. This is an exo hand. It's a wearable robot, what we call a wearable robot. It's all 3D printed, and Adam, you can see there, was wearing it. And the idea of this exo hand is that it's used for post-stroke rehabilitation. So it's fitted with both sensors and motors. And if you've had a stroke and you've lost hand function, the idea is that you would wear the exo hand on your real hand. The exo hand would sense how much force you're able to apply with your fingers, and it would apply additional force, give additional strength. And then as your fingers get stronger, the hand would then reduce the amount of force it needs to give you until, of course, you've recovered completely from the effects of the stroke. So again, it's a beautiful example of soft robotics, what we call wearable robotics, which I think is a very, very important new field of robotics. If I was a wealthy man, I'm not, but if I was, then I would invest in wearable robotics. This picture here is another part of our work in medical and surgical robotics. And this is a rather complicated machine for helping surgeons to repair fractured knees. And in fact, I'm told that knee surgery is one of the most difficult orthopedic procedures. And this robot, you can see there are all kinds of actuators. It's a multi-dimensional, multiple degrees of freedom device, allows the surgeon to pin the different pieces of the fractured joint and then position them and repair them with much greater precision than is possible to do manually, which is the way it is done at present. So then that brings us to robots designed to work with humans, and we have a lot of work in our lab. I'll just pause
like
there.
This pointing. Okay, giving you leg. Okay, what should I do?
Help.
Coming to help you.
And then it can do what it's been asked to do.
What should I do?
Wait.
Waiting.
Grasp.
Grasping. Waiting.
Release.
Waiting. What should I do?
So this is a beautiful example of a robot that's helping a human, Corinne, our PhD student there. The robot and the human here are doing a joint task. They're essentially cooperating to build a piece of, flat pack furniture. It's obviously a very simple example, but the important thing is that the robot is able to not only understand speech commands, but also can understand gesture. In other words, can tell if Corinne, for instance, were to put her hand up and go stop, the robot would recognize that gesture, which is very important, we think, in robot human communication. And in the pictures at the top of the frame, the slide, you can see that we also have an assisted living studio, which we use to test assisted living robots, robots that might help an elderly person perhaps live independently in their home. So assisted living, human-robot interaction is a very important part of the work of the lab, both for workplace assistants like Bert here, and for robots that would help elderly people perhaps live independently, as I said, or in an elder care home. So, and of course, another example of robots and humans working together is driverless cars. And we have a lot of work to develop driverless cars in the lab. Here are two examples of our vehicles. And what we're primarily concerned with in the work that we do on driverless cars is the human vehicle interface. So we're particularly interested in the psychology, the human factors. So how does it feel to be a passenger? This car, for instance, it's a pod. It has no steering wheel. It's completely autonomous. How does it feel if you're a passenger and the robot suddenly brakes very hard, or suddenly turns left when you don't expect it to turn left? So we're very interested in really doing the deep research on the human factors, the human vehicle interface for this new generation of driverless cars that everyone that tells me are coming soon. I'm not entirely convinced, because I think the technology is still some way away. But nevertheless, it's a really important part of the research. And of course, most research in driverless cars focuses on the autopilot technology. Here, we're not developing the autopilot. What we're developing instead is an understanding of the human interface with the vehicle, which we think is just as important as the underlying technology. And finally, I'd like to share with you a little bit of research that I've been doing in recent years on simple ethical robots. So this little diagram here shows you an image of the videos that I'm going to show you in a minute. And the A robot is named after Asimov. So this is our ethical robot. And the H robot is pretending to be a human. So that's why it's called an H robot. And you can see that we have a hole in the ground, because not a real hole, it's just a virtual hole. And the A robot can sense the hole. The H robot cannot. The H robot is acting like a human, perhaps walking down the sidewalk, and a human is not looking where they're going. Perhaps they're looking at their smartphone, not looking where they're going, and the A robot must prevent the H robot from falling into the hole. Now, what's important about this particular experiment is that the A robot has inside it, it's called an EPUC. This is the EPUC robot. The A robot has a simulation of itself, the whole of the environment, and the other robot inside itself, and is able to anticipate the future. It's able to anticipate if the other robot is likely to fall into the hole, and then with some additional ethical rules, which look like Asimov's laws of robotics, actually prevent the robot from falling in the hole. So this is the experiment that we did, where the A robot has to prevent the H robot from falling into the hole. And you can see the A robot notices the H robot and deflects it. It's then perfectly safe. The A robot then also doesn't fall into the hole, but avoids the corner of the hole. And in fact, this works very, very well. So my student Christian did many experiments, and you can see it works extremely well. And when we wrote the paper, I said to Christian, I said, well, it looks a little bit dull to me. It's a little bit boring. Let's make it more interesting and add another robot. And this, we believe, is the first experimental trial of an ethical robot facing an ethical dilemma. So here, the A robot is faced with two humans, both heading towards the hole. And you can see the A robot goes to try and save this one, fails, goes to try and save that one, but it's too late. So in fact, both H robots fall into the hole, which is very strange because we know that the A robot is capable of saving one of them every time. In fact, it saves one of them then. So we think this is a very interesting experiment because it's the first experimental trial, if you like, of a very simple ethical robot facing a balanced ethical dilemma. So if you're interested in, of course, any of this work, there are lots of publications and you can find them on the publications webpage of the lab, or of course, if you'd like help to find them, please email me. I'm easy to contact. I'd be very happy to help you find any of these projects. So I'm now going to move to part 3 of my talk, so the final stage of my talk, and really introduce the idea of ethically aligned design. Now I'm going to start with some bad news. Of course, robots do, we do have robot accidents, and driverless cars, of course, have already caused a number of fatalities. And this one that happened in March 2018 in Tempe, Arizona, in the US, was particularly distressing because it was the first example of a driverless car causing a fatality of a pedestrian. And the pedestrian, Elaine Hertzberg, was pushing her bicycle across the road and was hit by this Uber operating on autopilot. And it was very distressing because it's unlikely that Ms. Hertzberg even knew that there was a trial of driverless cars going on. So in my mind, this is an example of not employing ethically aligned design. If it was responsibly engineered, well, firstly, you wouldn't be testing an autopilot on public roads. And secondly, you'd make sure that all of the citizens of the city knew that this software was being tested on public roads and consented. In other words, had an opportunity to say, yes, we're happy for those tests to go on, or no, we're not. So I'm just giving you one example of what I would regard as irresponsible or unethical robotics. So how is it that we trust our technology? Well, we trust our technology not just because it's cool and convenient, but because it's safe. And it's safe typically because of standards, safety certification, and regulation. And without all of those instruments, standards, safety certification, regulation, we will not trust, the aeroplane that we fly on holiday or when we travel for work. So building trust is a complicated process, and I just want to show you this diagram. I won't spend too long, but just to show you that we need to link ethics to standards, ethical principles lead to standards, and standards, I believe, are vital to, oh, I'm sorry, something happened on my computer. I'm back anyway. So standards are vital to regulation. And of course, with regulation and public engagement and regulatory bodies, I believe we build public trust in our robots and our AI, our technology. Now, I've been involved for some years now in the development of new standards, ethical standards. The first one I was involved in was this one, BS 8611, which we believe, is the world's first ethical standard in the design of robots and robotic systems. So what is BS 8611? Well, it's basically a method for doing an ethical risk assessment. Risk assessment, of course, is not new. Engineers do risk assessment all the time. What's new about this is that we're assessing not just for physical risks, for safety risks, but we're assessing for ethical risks. And basically the standard articulates a set of 20 distinct ethical hazards and risks in a number of categories. And for each one of those risks, we give advice on how to reduce the impact of the risk and how you can measure, verify or validate that you've properly covered those risks. So let me now introduce the IEEE ethics initiative that I've been involved in since almost the beginning. The IEEE Standards Association, extremely well regarded around the world. Of course, you'll all be familiar with IEEE 802.11, which of course is Wi-Fi, very powerful standard, and the IEEE is a very well-known standards body. In 2016, they launched this initiative, and the first publication of the ethics initiative is this document called Ethically Aligned Design. It's publicly available. You can go onto the web page and download it. It's basically a document that sets out a whole series of ethical concerns and recommendations, ranging from general concerns to concerns about privacy, about affective, concerns about well-being, concerns about the environment, about sustainability, and a whole range of concerns. I think there are something like 150 different ethical concerns articulated in ethically aligned design. Now, in addition to publishing this document, we've also been spinning out a series of new ethical standards. Here are the first three: P7000, P7001, which I lead, and P7002, which is about data privacy. And here is a list of all of the first 14 of those standards. What's really important is that these are standards addressing really serious ethical issues in artificial intelligence. Things like transparency, which is the one I'm working on. Privacy is obviously very important. Algorithmic bias, which I'm sure you're all familiar with. Standards here on child and student data governance, employer data governance. Interesting, as we get down to the bottom, P7011 is really a standard on fake news. That's interesting, isn't it? P7013 is a new standard on face recognition technology. So we believe these are very important and timely new, new standards. I mentioned that I'm leading P7001, which is a standard on transparency. The basic principle behind this standard is that it should always be possible to discover why an autonomous system behaves in a particular way. And going back to the Uber accident that I that I mentioned earlier, if we don't have transparency, we cannot find out why accidents happen. So, I believe that transparency is really, really important and that all autonomous systems should be transparent, especially those that are critical systems, and that means not just safety critical, but ethically critical too. So I think I'm more or less running out of time, but I just wanted to point you to a paper that I published with my colleague Marina Girotka at the University of Oxford on ethical governance. So if you're interested in this question of how to link ethical governance and trust, then I can recommend this paper. It's open source, so you can download that. And that really brings me to the end of the talk. So there's just a little picture you can see of the lab. It's a very large lab that we have here in Bristol, around 200 faculty and students currently. And I just wanted to credit the many colleagues who've contributed to the different projects in the lab. If you're interested in learning a little bit more about robotics, I have a book published with Oxford University Press called Robotics, A Very Short Introduction. And more recently, earlier this year, I published a short paper in Nature Electronics about ethical standards in robotics and AI. So if you're interested in that particular aspect that I've been talking about, please have a look at this paper. So that brings me to the end. So thank you very much indeed for listening. I'd be delighted to answer some questions now.